Section 21.3 is a short section. So we see that more frequent compounding yields more interest, but there's a limit to the amount of compound interest earned. And the last column in this table that we also saw in the last section shows that limit. So in this section we'll look at compounding continuously. First, let's look at an example of what happens as we increase the compounding frequency. So this chart shows what happens if we have an initial balance of $1 and a nominal annual interest rate of 100%. So if that is compounded once per year, then after 1 year we'll have $2. If it's compounded 10 times per year, then after 1 year we'll have $2.59. If it's compounded 100 times per year, then after 1 year we'll have $2.70. If it's compounded 1,000 times per year, we get $2.72 if I round that up because I've got a 6 in the third decimal place. If it's compounded 1,000,000 times per year, then rounding up again, I also get $2.72. So we can see that these numbers get higher but closer and closer together the more often we compound per year. So as m increases, the amount after 1 year gets closer and closer to a special number which is called e, and that's equal to about 2.71828. Your calculator might have a special button for this number e, or you can just enter it as 2.71828. Continuous compounding is the method of calculating interest that yields what compound interest tends toward with more and more frequent compounding periods. So for a principal P deposited in an account at a nominal annual rate of R and compounded continuously, the balance after T years is going to be given by this formula: A equals P the principal times the number E to the power of R times T. So that's a pretty simple formula, and let's take a look at an example of calculating continuously compounded interest. So suppose we put $1,000 in a savings account with a nominal annual interest rate of 10%. How much will we have after 1 year if the interest is compounded daily and if the interest is compounded continuously? So first, let's write down what we know here. My principal amount P is $1,000, and my nominal annual rate R is 10%, so I'll put a 0 out front here, 10%. And to convert that to decimal form, I'm going to take my decimal, move it 2 places to the left. That's going to be 0.10 in decimal form. Now, for my interest being compounded daily, my formula for that is going to be A is equal to P times 1 plus R over M to the power of M times T. This is from the last section. Here I've already got what P and R are. M is the number of times per year that interest is compounded, so if it's compounded daily, that's going to be 365. And then T, I want to know how much I'll have after 1 year, so T is equal to 1 for 1 year. So then, compounded daily, I will get my amount at the end of the year will be $1,000 times 1 plus 0.10 divided by 365 to the power of M, which is 365 times T, which is 1, and that will give me $1,105.16 after 1 year. What about if my interest is compounded continuously? Well, then my formula is going to be a is equal to p times e to the power of r times t. And I've already got all those numbers figured out, so my p is $1,000. And then I've got the number e to the power of r, which is 0.10 times t, which is 1. And that's going to be equal to $1,105.17. So that's how much I will have if interest is compounded continuously after 1 year. And you can see that the difference between compounding daily and continuously after 1 year is only 1 cent, so it doesn't make that big of a difference in this case. So the things you should know for this section: you should be able to calculate continuously compounded interest given the principal and the nominal annual rate. You should know that continuously compounded interest is the amount that would be approached if interest was compounded more and more frequently.